First things first, it was pointed out before class that the schedule has the test on Wednesday. And I'm sure it's because I checked last week. Somehow I had in my mind that it was next week, because last week it would have been next week, and somehow I still had that in my mind. And I am simply not ready to give you a test on Wednesday. Right? I would have to be doing a review lecture today if I was going to give you a test on Wednesday, and I'm not ready to give you a review lecture. I'm ready to talk about redox reactions. So I've been thinking this through in the last 3 minutes as I've been panicking, and I believe that I can have one final lecture on chemistry on Wednesday, and then a review lecture on Friday, and give the exam Monday of next week. Is that acceptable?
Wait, does that say 7:19 a.m.?
That's when I uploaded this, yeah.
Oh, sorry. I thought it was like exam. Yeah.
Okay, so we will have the exam on Monday, March 26th then? Is that right? Because today's the 19th, right? And since we're going to be doing astronomy soon, what is happening at the end of chapel tomorrow? Winter will end at the end of chapel tomorrow. Yay! Like that really makes a difference in your life, you know. But it's at 11:15 tomorrow morning that winter ends and spring begins. Why? Because that's when we are at the spring equinox. The equinox is when the sun is passing over the equator. So that's why there's a specific time, there's a moment when spring begins, when the sun crosses the equator. You're all excited, right? Yeah. Yes, if it was warm and sunny and we were out playing baseball, we'd be more excited. All right. Let's get into chemistry things here. We've talked about acids and bases. We did the lab last week on acids and bases. I don't know why I didn't remember this. Obviously, the grapefruit juice didn't work very well because the grapefruit juice is already colored. And I think the color of the grapefruit juice dominates anything that was going on with our little cabbage broth. For some reason, I don't think the cabbage broth worked as well as it did a year ago. You know, maybe it's because I cooked it too long or let it sit too long after it was cooked. I don't know. But we tend to use a chemical reaction that changes color to tell us how acidic or basic something is. What was the basic premise of acids and bases? What does it mean if something is more acidic? Okay, more acidic means a lower pH, and the pH is measuring the concentration of the hydronium. That's H3O plus, but there's that funny minus sign in there. So a lower pH means a higher concentration of hydronium. And so higher concentration of positive ions is what it was to be acidic. Basic was just the opposite. Basic was a bigger pH or a lower concentration of hydronium, which translates to a higher concentration of hydroxide, which is OH minus, the negative ion. And we had what I have here in blue. Acids donate protons, bases accept protons. So something like HCl. In HCl, the chlorine will give up its hydrogen, so it's donating a proton. And a base will accept that proton. Now we're going to go into, well, you've already seen this chart and you've done the lab with this. I want to go over this last thing I talked about in class on Friday, just with a little more care. So this one here was just saying, what does it mean to have, quote, acid rain? Obviously, acid rain means that the rain is acidic. but we set a level of a pH lower than 5. So it's pretty reasonably acidic, not just very mild. And the acid rain is produced by, notice the G in parentheses, that means gaseous. By sulfur gas, well, sulfur, SO2, sulfur dioxide gas, in the atmosphere that combines with oxygen to produce this SO3, that would be sulfite, right? And then that sulfite combines with water to make hydrogen sulfate or sulfuric acid. And so you have sulfuric acid falling from the sky. And everybody's probably heard of sulfuric acid. They know that's not good. And so that's what acid rain is. Produced by our burning things, burning coal and oil. So in our water, one of the wonderful things about how God created this world is that carbon dioxide in the air will be dissolved into water, and in that water, it will form a carbonic acid. But if you put calcium in the water, that carbonic acid will react and form a solid rock, calcium carbonate. And so you have a rock that's in water that's calcium carbonate that is essentially taking carbon dioxide that was in the atmosphere and depositing it as a rock. So that keeps the atmosphere with a relatively low content of carbon dioxide. If we didn't have liquid water, we'd have much more carbon dioxide in the atmosphere. Now, we've already talked about global warming and the effects of water vapor and carbon dioxide vapor in global warming. The amount of carbon dioxide in the atmosphere would be much, much higher if we didn't have the water bodies. There is a temperature effect to this. Higher temperatures makes the water so it can't hold as much carbon dioxide. It will release carbon dioxide. So as temperature rises, the water will release carbon dioxide. Now, the textbook points out it should be no surprise that the amount of carbon dioxide in the atmosphere has been rising because we as humans have been producing a lot more carbon dioxide. We do things, we burn stuff, we burn gasoline, etc. Not only does that put the sulfur up there that makes the acid rain, it releases a lot of carbon dioxide. The amount of carbon dioxide in the atmosphere is not rising as quickly as we are dumping carbon dioxide into the atmosphere. Why would it not rise as quickly as we're putting it in there? That's kind of like saying, I'm pouring water into this barrel, and the amount of water in the barrel is not rising as quickly as I am pouring water in. What would have to be happening in that case? But okay, just to make it real clear, I have a barrel that has, let's say, 2 gallons of water in it, and I pour in another gallon of water, and now it has 2.5 gallons of water. What had to happen?
Something was transformed into something else.
Okay, something was transformed, or what I was looking for was something's leaking out of my barrel somehow. And what's happening with our atmosphere is the water absorbing a lot of that carbon dioxide that we as humans put into the atmosphere. So that the amount that it's going up is not as rapid as you would expect because of the waters. Now, we looked at this picture before. I wanted to focus on this. The pictures I showed you before didn't have the words with them. Water does a lot to counteract the effects of acid rain because of the calcite rock that's stored in the water, the calcium carbonate that's stored. If you put acid into that, the acid, the sulfuric acid in this case, will react with the calcium carbonate, and calcium carbonate will neutralize the acid. An acid and a base, when they combine, will neutralize. And so what happens is you start eroding, it calls it limestone here, the calcium carbonate. You start eroding that calcium carbonate to neutralize the acid in the acid rain. What's that going to do? Well, that keeps the lake water So it's still fine for life, that the lake doesn't become a big acid pool, because that would be kind of bad if the lake became a big acid pool. So normally we have some protection because we absorb that calcium carbonate in a body of water. But what if the rock and the lake bottom doesn't have much calcium carbonate? Then what happens? Then the pH is going to drop and it becomes acidic. And you can see the pretty tree now is just a shell of what it was because of the effects of the acidic water on it. So depending on your situation, bodies of water may become acidic or they may not. And it's if you have the calcium carbonate there. Our oceans maintain a pH. What would you tell me about that pH? Is that acidic or basic? It's basic because it's higher than 7. 7 would be neutral. Lower than 7 is acidic. Higher than 7 is basic. So you nailed it. So the ocean here tends to be a little basic. Why? Well, it's got all of that carbon dioxide that it's stored as calcium carbonate to keep it in a more basic state. The fresh water tends to be closer to an acidic here. You see pH less than 7. All right, moving to new material. Sadly, Chuck Friedline, my former colleague, died about 5 years ago now, something like that. No, it was more than that. It was before I got married. It's been a while now. But he was famous among Union College graduates for him taking a very common phrase having to do with oxidation and reduction and writing a song. And that song is Leo the Lion Says Grr. Now, I learned Leo the Lion Says Grr when I was in high school chemistry class, and you guys may have as well. It's a common phrase to describe redox reactions. Redox means reduction, oxidation. Obviously, the words are in opposite order for redox. So what's the difference between a redox reaction and an acid-base reaction? Acid-base reactions, we were talking about a transfer of protons. Redox reactions, we're talking about transfer of electrons. So it's what we're talking about, the transfer of, that makes the difference in an acid-base interaction or a redox reaction. So here's examples of oxidation and reduction. So here we have 2 sodium atoms. And 2 sodium atoms, through magic, became 2 sodium ions. Did they lose electrons or gain electrons to become sodium plus? It's still sodium, so what does that tell you about the number of protons? It's the same, right? Because the sodium tells us that it has 11 protons. Oh, I should know that. It tells us that it has 11 protons in the nucleus. So we have the same number of protons, but it has a +1 charge, which means that the electrons must have dropped by 1. And so it lost electrons, and that's an example of oxidation. So you have lose electron equals oxidation. So that's Leo. Lose electrons, oxidation. Now the second reaction is a chlorine. We have Cl2, fine little molecule, and now it magically undergoes a reaction where it becomes 2Cl minus. That's 2 atoms of Cl minus. Well, it's still chlorine, so it still has the same number of protons, but with the negative charge, that means it must have picked up an electron. So there it gained electrons. Gain electrons is reduction. Hence our song, Leo the Lion Says Grr. That's all, so we remember Leo, lose electrons, equals oxidation, and gain electrons equals reduction. And if I was Chuck Friedline, we'd all be singing, Leo the lion says grr. Leo the lion says grr. And then there's a lot more that I don't know. I know it's got some gain electrons oxidation. But he had sheet music. He had all 9 yards. So can you identify an oxidation versus a reduction reaction? A couple people are confident. A couple people are about ready to give it a shot. Here's the full reaction. Sodium plus chlorine gives you 2 sodium ions and 2 chlorine ions, and then what are they going to do? They'll form the sodium chloride salt with ionic bonds. So in this reaction, we had both an oxidation and a reduction. In this reaction, which one of those 2, sodium or chlorine, was oxidized? You have an answer of chlorine, a couple answers of sodium. So let's just go through our mnemonic. Leo the lion says grr. I said oxidation, so which one of the words is that referring to? Leo, is this yours as well? Actually, this is yours. It has your name on it.
Oh, that's mine.
Is yours? So lose electrons, oxidation. So we're saying which one lost electrons? If it loses electrons, its charge becomes more positive. So which one became more positive? The sodium. Hence, the sodium is the one that was oxidized. The chlorine, what was it? Reduced. Basic rules for what's going to be oxidized and what's going to be reduced. This graph with its pretty colors gives us exactly the same information, except for with pretty colors instead of with numbers, that we had when we looked at the electronegativity chart. Things with a high electronegativity really want electrons, and those were in the top right corner of the periodic table, not counting the noble gases. So fluorine is the most electronegative. It's the one that wants the electron most. Hence, it's the one that is most likely to gain electrons. Gain electrons, reduction. It's the most likely thing to be reduced. On the other hand, francium was the thing that had the least care about its electron. It's the most likely to lose its electron. Lose electron, oxidation. So the francium is the most likely element to be oxidized. So where's francium in this diagram? Francium is right here. Where's fluorine? Fluorine is right there. And yeah, they both start with F. Yay. It's kind of useful to know that. Now we use the term oxidizing. Why do you suppose we use the term oxidizing? Yeah, oxygen, yes. Because oxygen often causes something to be oxidized. Remember, oxygen is right there next to fluorine. It's the one right next to fluorine, so oxygen is right here. So oxygen is likely to gain an electron. Gain electron, which one is that? Gain electron. Reduct. No. GE, GER.
Oh, yeah.
Gain electron reduction. So oxygen is going to be reduced. We call it an oxidizing agent because it's going to oxidize the thing that it interacts with. And so that happens a lot. Like let's say we have iron and we have it in an environment with oxygen. that oxygen is going to have a reaction with the iron that takes the electrons away from the iron and gives them to the oxygen. So the iron is oxidized by the oxygen. That's why we have the term oxidizing. So an oxidizing agent is something that's going to get reduced. A reducing agent is something that's going to be oxidized. So we have this table about what oxidation and reduction are. Oxidation loses electrons, right? Leo. Reduction gains electrons, Gur. Another way is to say that something that is undergoing oxidation is going to gain oxygen. So iron, if it's oxidized, it's going to gain oxygen. Why is that oxidizing? Well, the oxygen comes, takes the electrons away from the iron, they go to the oxygen. The iron then lost electrons and it was oxidized. So gained oxygen by, well, along with the process of gaining the oxygen, losing electrons. Reduction will be just the opposite. If I take rust and I reduce it, I would be taking the rust and removing the oxygen from it, getting back the iron, instead of having iron oxide, the rust. And then a final thing, losing hydrogen is oxidation. But we already talked about losing hydrogen, except for it was losing protons. What's the difference in losing hydrogen and losing protons? What's the difference in a hydrogen atom and a proton? Hydrogen atom is made up of one proton and one electron. So the difference in the proton, remember an acid is something that is going to be, we had bad bases. Oh boy. Bases, something, acids donate. Acids donate a proton. What was the A in bad? Absorb. Bases absorb the proton. Acids donate a proton. So when you say donate a proton, that's different than losing a hydrogen, because the losing a hydrogen is losing the electron with that proton. So now the actual test, the only clicker question of the day. What element within the reactants is oxidized in the following equation, and what element is reduced? So I will write here our mnemonic. Leo, the lion says, Gur. All right, we're all in. There's the answers we had. Oddly enough, it shows the polling is still open even though this is done. Not sure why. I don't know what happened, so I'm just saving it now before something untoward happens. Rachel Hammond. Give us some clear education on here. You chose iodine. Well, you chose 6 out of 8 people. I don't know if you chose iodine is reduced. Is that making sense to you?
Yeah, I chose that one because it has a negative charge on the right side, whereas bromine it goes from negative to positive charge.
Okay, so the iodine, did it lose an electron or gain an electron? If it goes from a charge of 0 to a charge of -1, it gained an electron because electrons have a negative charge. So that would be in agreement with what you said. It gained an electron, so it was reduced. Right, that's what you had said. And then if we look at the bromine went from -1 to 0, so it has a positive charge change, which is losing an electron. And so that goes with oxidized. So that was the correct answer. You had the iodine gained an electron, so it was reduced. The bromine lost an electron, so it was oxidized. Yeah. Bromine. How can we use this? Well, batteries and fuel cells. Eddie Murphy, back when I was in high school, he came out with his Delirious album. And as a high school student, that was the funniest thing I'd ever heard. As an adult, I realized it's highly inappropriate. But as a high school student, I wasn't very refined to what's appropriate and what's not. And anyway, in one part of that Delirious album, he talks about cars that talk to you. And, he was in his friend's car. Ding! Your lights are on. Ding! Turn your lights on. Anyway, and then he says, in the hood, our cars speak to us differently. Ding! Say, man, your lights is on. Ding! What is you, deaf and blind? Turn your lights on. And then goes one step further. Ding! Say, man, someone stole your battery. I say we go get the person. That little piece of comedy made me change the pronunciation from battery to battery. So just so you know why I say battery half the time. The other half the time I'll say battery. A battery is a battery of cells, voltaic cells. So we're going to talk a little about voltaic cells. Yes, do not put on your potential test question, why does Dr. Webb say battery instead of battery? Right? That would be not on topic. Yeah. Just like my repeating 4 lines from his Delirious albums, probably not on topic. So voltaic cells are things that use redox reactions to make electricity for our use. We like those. I carry in my pocket here this little radiating device that might cause cancer someday that has in it a battery. A whole bunch of little cells, in this case they're lithium ion cells that produce a voltage difference through a redox reaction. Then we have the fuel cells. Fuel cells are a different thing from a battery because they actually have chemicals that you put into them that cause the redox reactions, and they'll just keep running. You put in more chemicals, they'll keep running. It's kind of like the internal combustion engine. You put in the fuel, it burns the fuel and exhausts. The fuel cell, you put in the fuel, it undergoes a chemical reaction, burning is a chemical reaction, and produces exhaust. And as the book points out, that's what we have in things like the space shuttle to produce its electricity. The fuel cell technology is much more efficient than batteries. I don't know if you guys read the textbook, but I did. And the textbook talks about, so if we use fuel cells in our cars, only 3 kilograms of hydrogen fuel will get you 500 kilometers. Sounds great. except for one little problem. 3 kilograms of hydrogen gas at standard temperature and pressure would take the volume of 3 cars. So you'd have to be pulling this big trailer if it's at standard temperature and pressure. Now you can compress it, but then it takes energy to compress the gas. And there is also just a little bit of a safety concern with having all of that hydrogen gas. Because hydrogen can easily react with oxygen, which is why it works really well for the fuel cell, in an exothermic reaction. What did it mean if there was an exothermic reaction?
So it exerts, right?
It exhausts. X means out. Therm is... No. That endo was the end. Yeah, therm is dealing with temperature. It exhausts higher temperature energy. Exothermic reactions give off a lot of energy. That's what bombs do, right? Bombs give off a lot of energy really quick. And if you burn hydrogen gas, it's an exothermic reaction. It's hot. That goes really quickly. Hence, it's kind of dangerous. So nobody wants to get in an accident in their car and then be the marshmallow over the campfire, or inside the campfire, as the case would be. So there's some inherent problems with fuel cell technology. Of course, when you're in the space shuttle and something goes wrong, well, you were going to die anyway. So you're not as worried about, oh no, we've had a terrible crash, because you're going to die in the space shuttle if you have a terrible crash, no matter what you did. So let's talk about how we harness this energy. So ions, you have to have the flow of charge if you're going to be able to use electrical energy. So this is an example of a type of voltaic cell. You have iron here in one liquid, and you have a penny, which we pretend is just copper, in another liquid. And these liquids are, of course, not just plain old water. You have something else in the water, like you see this here shows chlorine minus in the water. And then you're going to have chemical reactions that are going to make electrons flow through the wire for the chemical reactions to occur. Now this picture is not fully clear, but you notice positive charge. You have the iron is going to be going from the nail into an aqueous state with a positive charge. And so you get a positive charge that will attract electrons. So electrons will come into that iron nail from the light bulb. And the chlorine, on the other hand, builds up a negative, or the copper builds up a negative charge. And so electrons are going to go like this from the copper to the iron in this situation. As they go through that light bulb, we have the electrons going through a wire. It's going to take away energy from the electrons and give off light. Here is a more detailed picture showing how we can make this process continue. It has what we call a salt bridge, something to allow charge to flow between these two. Because what would happen if you connected this is you'd have a little surge and then nothing, because you would simply have this side would have attract electrons, this side would have given them up, and it would reach equilibrium. This little salt bridge is going to allow charge to pass from one side to the other. And so here we see the details of the reaction. We have iron that leaves the surface, and when it leaves the surface, 2 electrons are freed. Over here, we have 2 electrons come to a copper and allow it to leave free. And so iron produces iron 2 plus 2 electrons over here. Copper 2 plus absorbs the 2 electrons to give you copper neutral. those are the reduction and oxidation reactions that are occurring. So I know it says oxidation here. Here. Now it doesn't say oxidation or reduction. And you would never remember which was which. Flip them all around. Did the iron gain electrons or lose electrons? It lost electrons because the iron became more positive. And it shows you plus the 2 electrons that it lost there. There's another way to identify it. But I wanted to focus on looking at the charged state of the iron. So lose electrons, oxidation. Hence why that said oxidation. The other side, the copper, as you can see, it gained electrons. So that's reduced. Now here's a picture of a dry cell. A dry cell, that's pretty much your typical, if I get a AA battery, it's probably something like this. This has a graphite rod in the center. It has a zinc anode on the outside, and inside it has this paste made up of ammonium chloride, zinc chloride, and manganese oxide. It's a lot of chemicals, right? Well, we are studying chemistry, so we probably should be a little comfortable with the chemicals. But what's important here is that we're going to have reduction and oxidation reactions. So at the bottom center there, it's showing us the oxidation reaction. The zinc is being oxidized, producing extra electrons. And the graphite is being reduced, absorbing electrons. So we have electrons that flow through this circuit because of those reactions. And this paste is conductive to allow the charge to keep cycling. Here's something important about batteries. Remember, I'm a physics teacher. Batteries don't store electrons. They store energy, and they will give energy to electrons. And they act like a pump to pump electrons. But they don't store them. They move them. Cathode is the term we use for the positive electron. So if I have a battery, remember I said a battery is a battery of cells. What that means is in that we have a bunch of little cells. I'm drawing these as like AA cells. And then we have a post, and we have another post. So the cathode is the positive electrode. That would make, my picture has the colors all wrong. Let me change the colors. Good question. Better question is why I chose to put black there. If that had been the right one, I wouldn't have. Anyway. Okay, electrode is the contact where you have the positive or negative charge. So electrode just means your contact on the battery. And we have one that's black and one that's red here. And I believe I have my colors right. The red one is the positive one that's named the cathode. So cathode, cat, is positive. The other one is called the anode with the negative charge. We tend to use those colors black and red, And of course, I didn't look at anything before class. I'm like, why would I? But I'm pretty sure we use red for positive and black for negative. And so those are just telling us about where we're going to have oxidation and where we're going to have reduction. Looking back here, on the side that is producing extra electrons, that's of course got the negative charge. And the one with the negative charge we call the anode. The one that's absorbing electrons is the positive charge, that's the cathode. And you can actually see on your little single voltaic cell, notice this has the right term, voltaic cell, probably because that's the right term, that's the wrong term, because this is a single cell. A battery is more than one cell put together. The cathode is the positive one, and that's why your cell has a flat side and that little bump there. That little bump is where this is sticking up inside. And that's the positive because that's where they put the graphite rod. So that's why I drew my two cells here. This is a battery because it has two cells. A car battery has more cells. What's the nominal voltage in a car battery? Nominal means the number that we assign to it. Don't know. Okay, a car battery is nominally 12 volts. Voltaic cells, depending on what type of cell you use, produce somewhere between 1 to 1.5 volts. If I have a battery that's made out of cells that produce 1 volt for each cell, I'm going to need to have 12 cells to get to 12 volts. If they make 1.5 volts per cell, I can get down to what? 8 cells, if it's 1.5 volt per cell. And that would give me 12 volts. So the number of cells in a battery is actually kind of going to depend on how much voltage each cell produces. But a battery is a bunch of cells put together. So I already talked about the positive electrode was the cathode, the negative was the anode, and oxidation occurs at the anode, reduction occurs at the cathode. So those are important things about the battery. They're redox reactions. If you are producing a positive charge, the cathode, then you have to have the reduction. With batteries, we have rechargeable and non-rechargeable. You don't want to get those confused. What happens if you put a non-rechargeable on a charger? Does anybody know? I don't think it breaks the charger so much as it breaks the battery. You can make the battery explode or the cell explode if you try to put a non-rechargeable battery on. Because when you try to use when you use a recharger, what the recharger is doing is it's forcing electrons to go the opposite direction, which means it's trying to force the reversal of that redox reaction. Well, some cell designs, yeah, you can just reverse the reaction. You can make it run in the opposite direction. And some you can't. The ones you can't, you're going to build up gases. That is what can cause the explosion. So that's why you don't want to take non-rechargeable batteries and put them in a battery charger. And so the kind of batteries we have in our cell phones, well, they're lithium ion. Lithium ion batteries, I always think of them as lions. It just says lithium here. Those are rechargeable batteries. Every time you recharge, you're reversing the chemical reaction. But when you recharge and reverse the chemical reaction, you know what? It doesn't perfectly reverse it. You're always going to have just a little bit of loss. If you take a traditional car battery, the car battery has these lead plates. And, well, I think it has zinc plates as well. I'd have to look at it. But it has these lead plates. And as you use the battery, the lead plates give up lead to go into the solution. Just like here, you had the iron is giving up iron atoms that go into the solution. So if you have that battery running for a while, your nail starts to be degraded because a lot of iron has left it. When you recharge the battery, you reverse that process, and the metal comes back to the electrode. So when you recharge your car battery, what you're doing anytime you drive your car, then you're putting the lead back on the plate. But you're not necessarily making the plate nice and uniform. You might have had a plate that started like this, and then you took out chunks. So here's some chunks that got used up. And then when you recharge it, that material is returned, but it doesn't return to the same place. And so your surface can get more and more gnarly looking. And you can get places where, you know, you've eroded from both sides and you now have a hole in there. You have degradation of the surface. And that degradation of the surface is going to affect the efficiency of the battery, how well it can charge, how well it can discharge. So over time, they're going to degrade. Hence, with your cell phone, you only have a finite number of charge-discharge cycles. I heard somebody say it's around 500 times. You can completely charge, completely discharge your battery about 500 times. After that, it's pretty much no longer going to be very effective because of the degradation that occurs in the charge-discharge cycle. And there are conflicting things I've read, but I think in general, if you just keep, like I have a laptop at home, which I only use as a laptop like once a year. Otherwise, it sits on my desk. Well, it sits on the desk on the charger. If it's on the charger, what's happening with the battery? It's just constantly staying fully charged. So the battery's not going through any use and recharge cycles in that case. And we do have circuits in our computers to just keep them fully charged and to not have the batteries overcharged, that would be bad, or to have them use power and then go back up.
Yeah, that's what I was going to ask, because I know that there's some laptops you can charge, and once it's fully charged, it just stops. Like, in a sense, like, from what I learned from the Samsung phones is that before they had that issue of when they would leave the phone on the charger, it got super hot. So then as time went on, they decided to, I don't know what they did in there, that basically once it reaches that fully charged, that it's going to stop, like, you know, trying to give off as much electricity or whatever it is. And then there's some laptops, even some of the newer ones, who still have that issue. Like one of my friends, he plugs in his laptop and then he said that he left it charging in too long, and he had to replace the entire battery because it got messed up because he left it charging and he just kept emitting more and more and more. And my laptop, once it gets full, it stops.
Yeah, and that would be the sophistication of the charging circuit, right? If you take the way your cell phone does its charging, you might have noticed that it charges really quickly from like nothing to 90%. And then going from 90 to 100%, it's really slow. So like the last 5% takes almost as long as it did for the first 95% of charging. That's intentional. It's because they charge very slowly for the last portion. Other things that it's like time up. Oh goodness. Other things that you probably noticed is it gets hot when you charge. The Samsung phone problem, as I understand it, turned out to be that they didn't give enough space for the batteries to expand when they're charging. And so they were being compressed when they were getting heated from the charging, and that's what was causing the problems. Okay, well, I'm out of time. Oh, so sad, because we didn't talk about the fuel cell. Here's the fuel cell. Have a great day. So yeah, I'll see you Wednesday.